Let's finish up the problem that we were working on. I just cleaned up my slide a little bit, and this should be where we were in the process of evaluating or finding the area enclosed by this limacon. So I'm going to clean it up a little bit again, and then I'll plug in my upper limit minus my lower limit to do fundamental theorem. Here, 2 times 1/2, those are just going to go away. They cancel each other out. But I'm going to go ahead and distribute that 1/2 through there. So I have 3 theta plus 4 times sine of theta plus distributing this 1/2 now. I have 1/2 the sine of the double angle 2 theta from 0 to 2 pi. So plugging in my upper limit, 3 times 2 pi plus 4 times the sine of 2 pi plus 1/2 the sine of 2 times 2 pi, if theta is 2 pi, so that's 4 pi, not theta, 4 pi. So there's my upper limit minus my lower limit, which is 3 times 0 plus 4 times the sine of 0 plus 1/2 times the sine of 2 times 0, which is 0. So this is a 6 pi. 4 times the sine of 2 pi is 0. The sine of 4 pi is 0, so the rest of that just goes to 0. Minus 3 times 0, that's 0. The sine of 0 is 0, and the sine of 0 is 0. So there it is. The area enclosed by that limacon is 6 pi. So see, even without a calculator, finding the area of a limacon is fairly easy. It's pretty straightforward. It is a little time consuming, so we find that we don't see these a whole lot being asked to be done by hand, but we do see them on the calculator active portions of the exam a lot. So we are going to see these, and this will go directly toward our BC score because this is a BC concept. One thing I want to say about these two trig identities before we work another example is notice there's only one small difference. There's not a lot to memorize here. If you have the sine squared of theta or cosine squared of theta, it is 1/2 times the quantity 1, either plus or minus, and it's only cosine of 2 theta. This is the only, whether it's plus or minus between those, is the only difference between those two trig identities. So again, not a lot to memorize. You just have to know that if it is cosine, then it's a plus sign, and if it is sine, it's a minus sign. That's really the only difference between those. So again, it seems like that you're having to memorize 2 more trig identities or remember them if you've had trig, but not really, because there's not very much difference in them. But just make sure that you do know these 2 identities because you will use them in this context. All right, so let's work another example. Find the area of the region inside the limacon, r equals 2 plus the sine of theta. All right, so again, when it comes to talking about limits of integration, it's really important that we recognize what we're dealing with. If we're dealing with a limacon and it wants the area of the entire region, then our limits of integration are really easy. They're 0 and 2 pi. Now let's suppose it said find the area inside the loop of this limacon. Well, that's different because, you know, if we were going to draw this limacon, this is plus, so it's lying on the positive end of one of the axes, either the y-axis or the x-axis. Since it's sine, it's lying against the positive end of the y-axis, and so we would have these 2 little loops here. They would be a distance of 2 on either side. That would be a positive 2. That would be negative 2. We would have a loop that would be a distance of 2. We would know that r equals 2 there. And then this would come on here, and we would know that, this is the case where a is greater than b, though. So this one would be flat. So the loop was a bad example here. Let's say this was 2 plus 3. sine of theta, just for my example here. Then we would go on and, this distance here would be a distance of 3. But you get the idea that we could find, based on the fact that this end of the loop is where r equals 0, and this end of the loop would be where r equals 2, and we could find, the angle measure starting at theta equals 0 and find out what the theta measure is when r equals 2, and that would be half the loop, and then we could take 2 times that. So you get the idea that as long as it's the entire region, those limits of integration are really straightforward, but if it's a portion of it, then we've got a little extra work to do to find our limits of integration. Our limits of integration are 0 to 2 pi, so we can do those fairly quickly. Remember, it's 1/2 r squared, there's r, there's squared, d theta. So a lot of algebra to kind of clean things up where you can find the antiderivative. 4 plus, we have 2 sine plus 2 more sine, so that's 4 sine of theta plus sine squared of theta. We've got to do our trig substitution for that term, so we could go ahead and do that here. 1/2 the integral from 0 to 2 pi. Notice I'm being real good with my notation. I'm not dropping my d theta. I'm copying down my coefficient and copying down my definite integral. So 4 plus 4 sine of theta plus, now we're going to do our substitution for sine squared, which we said was 1/2 times the quantity 1 minus cosine of the double angle measure, and that's d theta. So again, more algebra steps to clean it up. I don't want to rush through it too quickly, but you get the idea. 4 plus 4 sine of theta plus 1/2, I'm distributing this 1/2 now, minus 1/2 cosine of 2 theta. D theta. Gathering like terms, I have a 4 and I have a 1/2, so 0 to 2 pi. This is 8 halves, one more is 9 halves plus 4 sine of theta minus 1/2 cosine of 2 theta, all with respect to theta. Now I'm ready to find my antiderivative. I pop my 1/2 out front, antiderivative of 9 halves with respect to theta, copy my plus sign, copy my 4. What did I take the derivative of to get positive sine? That was a negative cosine. Notice my parentheses. This is 4 times negative cosine. This is not 4 minus cosine. So be careful. I'm going to copy down my minus sign, copy down my 1/2. And here again, find the antiderivative where u is 2 theta, du is 2 d theta. I'm off by 1/2. This is the integral of cosine of u du, identical to before because those double angle substitutions will wind up with a cosine of 2 theta for both of them. So this is 1/2 positive sine of u plus c. So I'm going to pick up the meat here of the antiderivative and pop it in here. We said u was 2 theta, and it's a definite integral from 0 to 2 pi. So again, clean it up one more time. 9 halves theta minus 4 cosine theta minus 1/4 the sine of 2 theta, all from 0 to 2 pi. Now I'm ready for fundamental theorem. That's 1/2 times 9 halves times 2 pi minus 4 times the cosine of 2 pi minus 1/4 times the sine of 4 pi. That's a 4. So there's my upper limit. The 1/2 distributes all the way through here. Minus my lower limit, 9 halves times 0 minus 4 times the cosine of 0 minus 1/4 times the sine of 0, and oops, that should be, there we go. So this is 1/2. Let's see, that 2 and that 2 will cancel, so that's 9 pi minus 4. The cosine of 2 pi is 1. The sine of 4 pi is 0. So I'm going to go ahead and go here. That is 0. Minus this minus and this minus. So I've already copied that minus down, but here's another minus. Minus 4 times the cosine of 0, which is 1, and the sine of 0 is 0. So we could clean this up again. This is minus 4 plus 4, so this winds up 9/2 pi. So there's the area of the region enclosed by the limacon. All right, so let's do an example. We'll get started on this example, which is a rose. We'll leave the limits of integration for last. We'll do the substitution form of it first, and then we'll find the limits of integration. Most of the time, I did not say always, I said most of the time, when you are asked to find the area of a rose, most of the time it's a calculator active question. That's not to say we couldn't do it by hand if we were asked to. So again, our formula, 1/2 alpha to beta r squared d theta. This is a rose. There is no plus or minus. It is n theta, where n equals 2. Remember, if n is even, then we have 2n leaves. So this is a 4-leafed rose. All right, so we're going to have 1/2. I'm going to leave the limits of integration for now. I'm going to plug in my r, and it's r squared d theta. Let's go ahead and clean that up a little bit more. 1/2, again, leaving the limits of integration for later. When I square everything here, I have 4 times the sine squared of 2 theta d theta. So again, for this part of it, I'm going to have to use one of those trig substitutions. Now, we have a trig substitution that says the sine squared of theta is 1/2 times the quantity of 1 minus cosine of 2 theta. For us, in this example, we have the sine squared of 2 theta. So this just says if this is a single angle measure, then the result is the double angle measure plugged into cosine. So we're going to take whatever angle measure is here, and we're going to plug it into that identity, and we're going to double it. So here's the trig substitution we're going to use for the sine squared of 2 theta. All right, again, we can clean this up. This 4 and this 1/2 become 2. So I have a 2 out front. And now this term cleans up to 1/2 minus 1/2 of the cosine of 4 theta d theta. And now again, I can distribute that 2 through there, and we have 1 minus the cosine of 4 theta d theta. So now the only question are limits of integration, and I'm going to save that for the next video. So look on the next video and we'll talk about limits of integration here.